everyone. Welcome to Kwiation Engineering YouTube channel. And today I'm going to do the lesson number 2, EASA Module number 8, Aerodynamic. Alright, so if you still not subscribe my channel, please subscribe my channel. And if you still not share my videos and share my channel, just share with your friends, relatives, and someone who like with the aviation, especially for aircraft maintenance. So, okay, so no need to waste the time. So let's go to the lesson. All right, so today I'm going to teach you about aerodynamics and aerofoils. All right. Okay, so the lessons content are number 1, aerodynamic and aerodynamic, mass flow and energy. And then the second one, aerofoils and aerofoils, aerodynamic forces, definitions, aerodynamic resultant, and lift and drag, factors affecting forces. Under factor affecting forces, you can see lift and drag coefficient and angle of attack. And then the center of pressure, under center of pressure, pitching moments coefficient, and the aerodynamic center, and lastly, downwash. All right, so let's go to the lesson. Number 1 is aerodynamics. Okay, so aerodynamic is the study of air in motion, which includes changes in the physical characteristics such as pressure and density. Thermodynamics is similar but in likely to involve in significant temperature changes. Because of the air is in motion, changes in velocity and mass flow rates are also important, right? So aerodynamic also involves the study of forces being generated. Example, the lift force on the wing, right? And so a brief mention you must make of some basic principles. All right. Okay, so the first one under aerodynamics, the first one is mass flow. So mass flow, you can see volumetric flow rate is given by A into V. You can see A is the cross-sectional area and V is the velocity, right? So you can say the cross-sectional area into velocity. So we can the units are cubic meters per second. So, and the mass flow rate is given by the density into cross-sectional area into velocity. So the units are kilograms per second. All right. So in a converging, diverging duct, you can see this is the converging and diverging duct, right? Converging, diverging duct, the mass flow rate must be constant. Remember, converging, diverging duct, the mass flow rate is constant. What goes in must come out. It means what the air goes in and it must comes out. And if density is unchanged, remember density is not changed, volumetric flow rate will also remain constant. This is shown by A1 V1. It means A1 is the cross-sectional area 1 and velocity 1 equal cross-sectional area velocity area 2 here, and velocity 2 is equal, right? So if the cross-sectional area changes, then the velocity will be changed. Remember, the cross-sectional area is changes, then the velocity is changed, right? Area reduces, the velocity, it means if the area is reduced, the velocity will be increases in the converging, diverging duct. So you can see this is the area is bigger than this is the area here, the area is smaller, so the velocity in here is smaller than the velocity in here, right? It means the V1 is smaller than V1 V2, right? Okay, so now we'll go to the energy. So this change in velocity implies a corresponding change in kinetic energy, right? Kinetic energy equation is half into mass into velocity square, right? V square. So the principle known as conversion of energy suggests that unless extra energy is introduced into a moving airstream such as fuel, the overall energy constant must remain unchanged from one point to another. Hence, if kinetic energy increases, some other energy form decreases. Remember, if the kinetic energy is increases and some other form energy forms will be decreases, right? So the Bernoulli's equations highlights the relationship between the pressure energy and the kinetic energy, right? So now you can see this is the pressure energy plus kinetic energy or dynamic energy equal constant. It is a constant, right? It example total P dot, right? Example, pressure plus half into mass into V square, right? So equal constant, right? You can see this equation. So this can be expressed as P1 P1 is pressure 1 plus half into R into V squared into 1. I mean V1 square, right? They don't mention is good, equal P2 plus this is the kinetic energy number 2, kinetic energy number 1. Okay, you can see this one. This implies that if V2 is greater than V1, if the V2 here, V2 squared, right? This is V squared, V2 squared, V2 is greater than V1, as in the throat of the venturi, then P2 is less than P1. It means if the V2 is greater than V1, then the P2 is less than P1, right? Just remember the relationship. There is a drop in pressure. So it means there is a drop in pressure, right? The meaning is like this, right? It means the pressure plus kinetic energy equal, it is a constant, right? It means even if there is less, if there is a decrease, there must be increase. So this is the constant, right? So it means these two are equal, P1 and P1 plus the kinetic energy in this P1 and P2 plus V2, this is equal. So if the velocity on this point increases, so the velocity in this place is decreased. But it means if the velocity is increases, so the pressure must be decreased. That is the thing. When you read, you can understand, right? Okay, this is of particular interest to students of aeronautics because the flow through a venturi has similar characteristics to the flow over an aerofoil. The aerofoil's chambered shapes is virtually the shape of venturi. Bernoulli's equation showing the relationship between changes of pressure and velocity is used to explain the lifting effects of aerofoil. All right. Okay, you can see the high pressure, this is the low pressure, and again the high pressure. Why is the high pressure, right? So why there is a low pressure? Because the velocity is increases due to the area is decreases, right? So it means in here low speed, and the speed is accelerating flow, and this is the high speed, and then the flow is decelerating, and then again the low speed. There is low speed because why the area is increases. The pressure and speed, the air accelerates when the flowing from the high pressure to low one, and slows down when the flowing from low pressure to high one. Okay. All right. Now let's go to the number 2, aerofoils. There are several theories used to describe how a lifting force is generated by the action of air in motion past an aerofoil. Whatever the theory, the lift force results from a difference between the pressure acting in the upper and lower surfaces. All right. Okay, so now let's go to the number 2.1 aerodynamic forces under aerofoils. The diagram shows a typical pressure distribution around the aerofoil. So this is the aerofoil. This one shows the typical pressure distribution around the aerofoil. This can be determined by the wind tunnel experiment, where the pressures acting at several points on the aerofoil can be measured using manometers. The manometer will indicate the difference in the static pressure P acting at a particular point and the free stream static P0. This difference is P minus P0 at each point is plotted to give the distribution shown. The length of the arrows represent the pressure difference, right? You can see the length of the arrows shows the pressure differences. The direction of the arrows represent the sense. Towards the surface indicate pressure greater than static. Away from the surface indicate less than static. Okay, different distributions will result from different angle of attack. All right, you can see this figure. Aerodynamic forces result from the action of these aerodynamic pressures acting on the areas of the aerofoil surfaces. It is clear to understand the effects of these pressures by studying the diagram below. Here is the diagram, right? On these, the pressure has been plotted using the chord line as a datum, right? So this is the chord line as a datum. Note that the negative, it means that this side Okay, the negative suction pressure has been plotted upwards, and the difference on area enclosed between the two curves is proportional to the overall lifting effects of the aerofoils, right? You can go through this graph, right? This is the chord line and this is the pressure difference. Okay, the pressure distribution around an aerofoil. Now the definitions. Number 2, aerofoil is the term used to describe the characteristic shapes of the cross section of an aircraft wing. Okay, this is the aircraft wing and the cross section of aircraft wing, and whose purpose is to generate lift. Discussion of aerofoil performance is the main purpose of this module, and so some distributions and definitions of this shape will be essential. Note that the aerofoil section is considered with plane parallel to the relative airflow. You can see the aerofoil, the cross section here is the leading edge, and this is the chord line here, the chord line, this is the trailing edge, and this is the chord C, right? And this is this line and this line, this is the angle of attack here, angle of attack. This is the chamber and chamber mean line. Here is the chamber mean line and this is the chamber line. All right. So now the relative airflow, RAF. Relative airflow means is the movement of the air relative to the aircraft, right? Is the movement of the air relative to the aircraft. Or aerofoil, in practice, it is the aircraft which move relative to the air, but its aerodynamic theory and the wind tunnel experiment, it is the air which is considered to be in motion. Okay, relative airflow. And next one, leading edge. Leading is the foremost point of the aerofoil. This is the leading edge. Okay. And the trailing end is the rearmost point of the aerofoil. This is the rearmost point of the aerofoil. Okay, and then the chord line is the straight line is joining leading and trailing edges. There is a straight line. Okay, there's a straight line joining leading end and trailing edge. This is called the chord line. And the chord length, C is the length of the chord line. Chord length, chord C, the length is the length between the chord line. Okay. Length is length of the chord line, not between, right? So chamber line is the line drawn through the points equidistant from the upper and the lower circle. The chamber line is usually curved line. The greater the curvature, the greater will be the aerodynamic forces generated. Remember about this, okay? And now the thickness of an aerofoil is the greatest distance between the upper and lower surfaces. It means the thickness divided by chord ratio equal thickness divided by chord, normally expressed as the percentage. Okay, thickness divided by chord ratio. This one normally expressed as a percentage. Angle of attack, the angle formed between the chord line and the relative airflow, right? So this is the angle of attack. Angle of attack is the angle between the chord line, and the relative airflow. Okay, and the span B is the distance from the tip to tip, measured perpendicular to the chord line. Okay, aspect ratio is the span divided by chord. Maybe there's a questions can be asked from aspect ratio. What is the aspect ratio? Aspect ratio is span divided by chord. If the wing is taped, example, it has the varying chord, then the aspect ratio may be expressed as a span square divided by wing area. Now the wing area is the area projected into the plane perpendicular to the normal axis, and the stagnation point is the point on the surface of the aerofoil where the relative airflow has been brought to rest. Okay, remember. Now next one is aerodynamic resultant. So whether the student studied pressures or forces depend largely on the depth of his studies. It is simpler to consider forces, and this will be sufficient for much of this model. It has been stated that pressure acting on area produces a force. Remember, pressure acting on area, this is called a force. The force resulting from air in motion, in turn an aerodynamic force. The pressure distribution is then replaced by an arrow representing this force in terms of magnitude and direction. All right. So the line of action of the force determines the center of pressure. That point, center of pressure on the chord line through which the aerodynamic forces can be considered to act. Okay. So this one become like this, and a relative airflow is coming, and it goes like this. Okay. Lift and drag. Now the lift and drag. It is of greater benefits to resolve the forces F into two components which are defined as lift The component of aerodynamic force resolve perpendicular to the relative airflow, and drag is the component of force resolved parallel to the relative airflow. Right? This is so that variation of lift and drag associated with variation in angle of attack and chamber can be studied individually. It will be appreciated that the purpose of the aerofoil is to generate lift. Okay, the purpose of the aerofoil is to generate lift so as to overcome the effects of weight. The drag should be seen as an unavoidable obstacle into motion. All right. So now the factors affecting forces. Factors affecting forces. What factors affecting the magnitude of these aerodynamic forces? Clearly, the greater the area and the greater the pressure involved. What affects the pressure force? The greater the suction, the greater the lift. The suction P minus P0 will be greater when the static pressure is least, and this will occur when the velocity V is greatest. Summarizing, it can be stated that following on Bernoulli. So aerodynamic force is proportional to the fluid density. Aerodynamic forces is proportional to the fluid density into fluid velocity square into area of the body surface. It means F proportional to the half into fluid density into V squared into surface area of the body. Right. So similarly, lift and drags are proportional to the half into density into V squared into S. All right. Now, density, velocity, and area are all factors that affects lift and drag. There are a number of other factors, but only two more will be considered at this stage. Note that we have made a statement of proportionality. It is not an equation just yet. This will be derived by wind tunnel, the experiment. All right. So now the lift and drag coefficient. If an aerofoil is placed in a wind tunnel, test may be conducted to establish pressure distribution or to measure forces. Suppose the aerofoil area S is placed in the tunnel and air density R is drawn across the aerofoil at a constant velocity, then lift and drag forces will be generated. These forces may be measured on force balancing rig because it has been stated that forces changes as angle of attack will be measured as well. So remember that lift is proportional to these equations, right? So an equations may be formed L equal C half density into V square S by including some number or coefficient. Here the C is coefficient of lift. All right. So now from the experiment, L is measured and R, V, S are known, measured, and so C equal lift divide by half into R into V squared into S. So the coefficient used to form the equations has been deduced from the result of the experiment. It is worth noting that the term half into R into V squared is often replaced by Q. Therefore, C equal lift divided by Q. It means for all these sections we will name that as Q. So therefore the C equal lift divided by Q. The same can be done for the drag force. So there is a drag coefficient also, right? You can see this one, drag divided by Q. But we must clearly differentiate between the different cases and values of C. Right? Lift divided by this one Q equal the coefficient of lift, and here the coefficient of drag. Okay, this is the lift coefficient and this is the drag coefficient. The two other factors which affect the aerodynamic forces can now be included. It will be found by experiment that lift coefficient and the drag coefficients will vary or change when either angle of attack, this must be angle of attack, or aerofoil chamber, it means shape is changed. All right. Now the angle of attack. The factors affecting lift and drag have just been outlined. All can be determined by experiment, but changes in the force are generally deduced from the relationship between lift coefficients or drag coefficient. And this is not A, this is actually angle of attack. Okay, right? There should be an infinity mark, right? So these relationships are best shown graphically. The general shape of these graphs must be memorized by an aeronautical students. Okay, you can just go through this graph, like this is the angle of attack with the lift coefficient, and this is the angle of attack with the drag coefficient. You can see the movements of this graph. Okay, And now note how lift coefficient increases steadily and linearly as increase up to maximum, after which is decreased rapidly. Okay, this with this graph. Okay, and not how the drag coefficient is curved that increase steadily, but that the rate of increase become greater here, right? See, the rate of increase is become greater in the angle of attack with drag coefficient, but the angle of attack with the coefficient, it will increase greatly and then suddenly decrease. Okay, this is the thing they taught. If the experiment were repeated with aerofoil of different chamber or shape, the general shape of the graph would be similar, but the curves would be displaced vertically and or horizontal. A final but important point to consider in this section is the lift to drag ratio. Lift to drag ratio. So lift is what is required. It should be maximized. Remember, in normally the aerofoils, we need the lift, not the drag. Okay, so the lift is what is required. It should be maximized, and the drag is not required. It should be minimized. So for maximum aerodynamic efficiency, the lift to drag ratio should be as great as possible. It means we need lift, but we must reduce the drag. So lift to drag ratio must be greater as possible. So the ratio cannot be deduced directly by experiment, but lift coefficient and the drag coefficients can be derived as stated, and the ratio derived by division CL divided by CD. This ratio is then plotted against angle of attack. Okay, this is the symbol of angle of attack, not A. Right? So you can see this graph, angle of attack, lift to drag ratio. So this graph clearly indicates that the best maximum lift drag ratio generally occurs at the relative small angle of attack, typically 3 degrees to 5 degrees. Designers and operators endorse to operate any aerofoils at an angle of attack in this range as much possible. Right? You can see this graph. Right? This is the most efficient angle. Here is the most efficient angle, and this is the stalling angle. Right? So finally, a word is introduced that is of great significance: the stall. Look at the diagram. There is an angle of attack beyond which lift coefficient has reduced subsequently, and drag coefficient has increased markedly, and the CL lift coefficient has reduced. Okay, right. So this means that there has been a sudden loss of lift and a rapid increase in drag. The aerofoil wing is said to have stalled. It means if they are stalled, right? If the aircraft is stalled, there must be a sudden decrease of lift, and there must be a rapid increase in drag, right? So then the aerofoil wing is said to have stalled, and is the potentially dangerous scenario if it is occurs in flight. In flight, this scenario will occur. It is very dangerous. All right. And now let's go to the center of pressure. So the two components, lift and drag, have been shown to vary as angle of attack varies. But not only does the magnitude of the force vary, but the line of action, and hence the center of pressure changes. Okay. So as the angle of attack increases, remember, as the angle of attack increases, the pressure distribution changes shape, with proportionately greater suction generated towards the forward portion of the wing. This causes a forward movement of the center of pressure. This forward movement continues until the lift coefficient values start to reduce. At this point, the center of pressure now reverses its movement. It moves back as the stall condition is approached. Okay, so you can just see this graph, right? Angle of attack, this is the leading edge, fraction of the chord back, this is the trailing edge, right? So this is the quarter chord positions, and this is the position of the aerodynamic center, the movement coefficients about aerodynamic center. Okay, this is the thing that describes about these sentences, right? So I don't have time to explain, so you can just read this one and then you can see this graph. Okay, then you can understand what did they said. Okay, all right. So now let's go to the pitching movement coefficient. Pitching movement coefficient. So consider the diagram. This is the diagram which shows an aerofoil which can be considered to be pivoted at either A or B, right? The lift L would cause rotations about the pivot anti-clockwise or nose down about A, and clockwise or nose up about B, right? So rotation is caused by application of moment M which itself is dependent on lift L magnitude, right, multiplied by the distance of the center of pressure from the pivot. Okay, so from these it can be deduced that the strength and the sense of the rotations depend on angle of attacks and position of the pivot. So again, we rely on this to be illustrated graphically. Nose up is considered a positive pitching movement, nose down is negative, right? Nose up is positive and nose down is negative, right? Just as before, coefficients were introduced to create a lift and drag equations. So a pitching movement coefficient, Cm, pitching movement coefficient is introduced, M equal Q into SC into Cm. So pitching moment where C is the chord length, C is the chord length, it means the length of the chord, and Cm means the moment coefficient, right? Okay, so as with CL, lift coefficient and drag coefficient, it is usually to draw graphs using the Cm rather than M. You can see the diagram below, right? This is the moment coefficient Cm. Okay, you can see this is the graph. Moment coefficient is about the leading edge, and this is the moment coefficient about the point near the trailing edge, and this is the moment coefficient about the aerodynamic center. All right. Okay, now the aerodynamic center. Another interesting feature emerged. There must be some point lying between A and B, right? There must be some point between line A and B. Okay, right. Such that if the aerofoil was pivoted at that point, the pitching movement coefficient would be constant regardless of the angle of attack. So this point is known as the aerodynamic center, right? This point is known as the aerodynamic center. Example, the point on the chord line about which the pitching moment is constant. All right. So now the downwash. Here is the downwash, relative airflow is coming, right? The force reactions on air, then force lift on aerofoil. This is the downwash here. Now the upwash, stagnation, and downwash. So the flow of air around the aerofoil causes variation in speed and pressure that result in the creation of lift. Lift is the resultant force applied to the airframe considered perpendicular to the relative air force. From Newton's third law, there must be an opposite force applied to the air. These reactions cause deflections of the airflow as it leaves the trailing edge, termed downwash. Okay, you can see what is the term downwash. There may well be an upwash effects ahead of the leading edge. All right. Okay, so that is the end of that is the end of this lesson. So I think you understand about the lesson number 2, aerodynamics. So actually, thank you for participating this lesson, lesson number 2, aerodynamics module 8. So in the next lesson, I'm going to teach you about the drag. Okay, about the drag, and they have some lessons. So if you like this video, please hit the like button, and don't forget to subscribe this channel, because if you subscribe this channel, and then I will be motivated more and I can do more lessons for you. And the next lesson about the aerodynamics, I will going to do the drag, and the next upcoming lesson I will going to start about ATA chapter 21, the pressurization system. So you can stick with my channel. And again, thank you for participating in this lesson. And if you still not share these videos with your friends in Facebook, social media like Twitter, or like anything in social media, please share this YouTube channel. Then it will be helpful for someone who is interested about aviation, especially aircraft maintenance. All right, so let's meet on next lesson. Until now, have a good day for all of you.